5 times. 15.
Hello, hello. I don't know whether I'm coming through here or not, but in case you're wondering why did I do this book with Martin, Martin's a very unusual guy at Harvard. He actually is in the biology department and the mathematics department. I first wrote about Martin's work in '92 when he was modeling the AIDS virus in the body, and by about mid-noughties he'd written about 40 papers for Science and Nature, and I suddenly thought, this guy's incredible. He's an incredibly prolific scientist. We should do a book together, and this is the result. Now, these are also Martin's slides, so I should say, Martin, if you watch this on the web, I'm really sorry I mangled your beautiful mathematical ideas, okay? I'm sure I'm going to do that a bit. Here, we've got an interesting glimpse of very early life, cyanobacteria. We're talking about cooperation, and what fascinated me was that even in these primitive organisms, you get elements of cooperation, and you find here in these strings of single-celled organisms that maybe 1 every 10 will commit suicide to help nourish the rest. Now here, of course, we've got a much more human form of cooperation, the Good Samaritan, and so on. And it's a bit of an enigma. Why do we cooperate? Where does cooperation come from? So let's just put this in a kind of bigger context. Okay, Big Bang of creation. We know when that was 13.7 billion years ago. We can be pretty accurate about the birth of the solar system. Origin of life got going pretty indecently quickly after the solar system was born. Maybe it came from beyond the solar system. We can't really rule that out. Then we start off with the very earliest forms of life that we actually know of. The origins definitely go back before that. Bacterial life, 3.5 billion years ago or more. Then we get more complex cells, which is the first glimmers of, even with bee life, we get cooperation. But these are, when you've got a nucleus in a cell, eukaryotes, these are more complex. Then we get multicellularity about 600 million years ago, and that's when cooperation really gets going. And then we get this extraordinary thing here, human language. This is the second great information revolution in biology. Here, information was transmitted down generations by genes. Here, you can transmit information by language. Now, this looks rather boring. In fact, this is the thinking path of Charles Darwin. And in 1842, when he was just 33, he came up with the most astonishing insight. All life on Earth is related, and it all goes back to one origin. So the agenda for Martin has always been explaining cooperation using mathematics and using mathematical rigor. And of course, 20 years after Darwin, Wallace came up with similar ideas. Now, when you look at evolution, there's 2 recognized pillars of evolution. You've got mutation, things mutate, and they're slightly different, and in an environment, one organism or idea will thrive and be selected at the expense or do better than the others. And that's the classical picture of where all the extraordinary diversity of life came from. But we argue in the book that cooperation is the 3rd pillar of evolution. And without cooperation, there's nothing constructive really going on in biology. There's the first example I started with, where you've got even these filaments of cyanobacteria cooperating. Ant colonies are extraordinary cooperative ventures. Leafcutter ants, they invented agriculture 60 million years ago. You know, eat your heart out, Neolithic farmers and all that stuff. And then, of course, human societies are extraordinary. So Martin tries to frame this in precise mathematical terms, and he's talking about a donor paying a cost for a recipient to get a benefit. That sounds incredibly dry. What does he mean by this? If you stop someone and you're desperate to get somewhere, they're going to have to give you a bit of their time to explain where the bus stop or whatever it is. So you find that when you cooperate with people, you're always investing a bit of your time, your effort, or whatever, your fitness, that's the biological term for it, in that other individual. And this is really at the heart of, oh dear, the slide hasn't really come out very well here. This is a classic game theory way of expressing what the problem is with cooperation. prisoner's dilemma, because, I mean, this comes in loads and loads of formulations, but basically, two guys, say they are guys, arrested outside a house that's been broken into. There's a dead body inside. So perhaps one of them has murdered them. There's two crimes here. There's a murder, there's a break-in. If you cooperate with each other, you both keep your mouths shut, you're separated by the police chief, and he says, look, if you snitch on the other guy, I'll just convict you for the break-in. And in fact, if you snitch on them, I'll knock a year off as well. In fact, Martin's put this slide together, so being a very precise guy, he's put it in terms of years lost to reflect years of incarceration. But there's something very interesting here when you look at it, which is you find that if you both cooperate, you both keep your mouth shut, you spend 2 years in jail. If you cooperate, so you keep your mouth shut, and the other guy snitches on you, you end up 4 years in jail, he's only got 1 year, vice versa. And then here, if you both snitch on each other, you get a year off for being honest, but you're still going to moulder in jail for 3 years each. But you find if you analyze this, it's logical always for you to defect. You're always going to be better off if you defect. So that's the rational thing to do. But here's the dilemma. Of course, the other guy is thinking in exactly the same way. So you'll both defect, you'll both end up here, and actually, if you both cooperated, you both would have been better off. Now, what's interesting is that when you look at, if you model this in a computer, natural selection gives you the wrong answer. It will always go for the nature red in tooth and claw that you defect on the other guy. So you need a bit of help to cooperate. And it turns out there are 5 mechanisms of cooperation. One's really easy, direct reciprocity. I help you, you help me. And it was the great Robert Trivers who came up with this insight. And what he did was he played the prisoner's dilemma again and again and tried to understand, look at strategies and so on. The C's cooperation, D's defection. And he was trying to figure out, what's a strategy to play this game? Axelrod from the University of Michigan came in, set up computer tournaments where people were invited to come up with strategies to win this game. And what was fascinating was that tit for tat, really simple strategy, won the game not once but twice, devised by Anatole Rappaport. And basically, you start out cooperating with your opponent. If they cooperate, you cooperate back. If you defect, I defect. Now, people wrote quite elaborate computer programs, but they always lost to tit for tat. So that gave us one insight into how to play that game. But there's a problem with tit for tat. We all make mistakes and cock-ups. If you think the other guy is defecting when actually he's being cooperative, but you've got your wires crossed, then what happens is that as soon as he defects, tit for tat just triggers this endless round of defection and counter-defection and so on and so forth. So that doesn't quite work. So what Martin can do is he can simulate strategies in a computer. He can start off with a kind of random sea of strategies, and he can use Darwinian principles to let them evolve and pick, in effect, the winning strategies. And you find that if you have a sea of agents doing this, always defect, always wins initially, but there are always a few holdouts. Then the tit for tats come in and take over. You find it's very, very dynamic. Then you find you get something called generous tit for tat coming. And basically, that copes with this problem of if you make a mistake, which of course you will in evolution because things are mutating and evolving, if someone defects on you, you sort of forgive them occasionally. You think, okay, look, you've defected, but one time in 3 or something, I'm going to let you off. And that becomes a winning strategy. So, again, you run these things, you get to generous tit for tat. Then you find that as the population carries on evolving, you get sort of complacency setting in. I'm anthropomorphizing it. You get always cooperation. And in fact, if you run these things in a computer, you get huge cycles of cooperation and defection. And it's fascinating looking at economic cycles in the same way, or societies waxing and waning and so on. There seems to be something quite fundamental to this. But what's fascinating is that if you look at the strategies that win, they tend to be generous. This is, you can average the winning strategies over time, which is that they accept they're not always trying to get everything all the time. They're hopeful in that they tend to go in being cooperative, and they're forgiving in that when people defect, winning strategies will just let you off now and again, just to stop that endless retaliatory tit for tat. So That's the first mechanism of indirect reciprocity. Sorry, that was the first mechanism, direct reciprocity. Here's the second mechanism, indirect reciprocity. Now it's I help you and someone else helps me. And this is where the Good Samaritan comes in, because this actually tells us something fundamental about language. Reputation makes the world go round. We are obsessed by gossip magazines, reputation, and so on. When the Good Samaritan was operating, was helping someone out, he was thinking, what's that person going to tell other people? What happens if someone sees me being cooperative? And it turns out that there's a very fundamental relationship between our ability to talk and in the indirect reciprocity mechanism. And in fact, you can see how this drove the evolution of our big brains and our social systems, and they're all interlinked together in a kind of braid. And David Haig, one of Martin's colleagues, put it this beautiful way. For direct reciprocity, you need a face, tit for tat with that individual. For indirect reciprocity, you need a name. Fred was horrible to Harry, therefore I'm going to be horrible to Fred. Okay, second mechanism, neighbours help each other. It's actually much more subtle than that, but I shall speedily move on. Group selection, Darwin actually glimpsed this. This was very controversial until recently, but it's been proved in a computer mathematically, and if there's someone anti-multi-level selectionist out there, forgive me for saying that, there can be no doubt that a tribe including many members who are always ready to give aid to each other and to sacrifice themselves for the common good would be victorious over other tribes, and this would be natural selection. So the more cooperative tribe was the winner. And then finally, we've got kin selection. And this is where the ant colonies come in and so on. Haldane had the first insight, scribbled on a napkin while drinking beer in Bloomsbury. Hamilton fleshed it out in mathematical form. Martin attacked it, and there's the most almighty hoo-ha in the evolutionary biology community. If you get the New Yorker, you can read all about how he's not liked by many evolutionary biologists, but they all agree on one thing. This mechanism works because you cooperate with people who are genetically close to you. And so if you look at ant colonies, there you've got individuals that don't reproduce, but they're looking after the queen. Why? Because the queen is transmitting their genes to future generations. So that's where that mechanism of cooperation came from. We are amazing because we use all 5 mechanisms of cooperation. We are super cooperators. And the world needs super cooperators. And in fact, the final word is that we're not only talking about cooperation with each other in this generation. If you look at the state of the planet, we have to think carefully about cooperating with future generations too. And that's it. Thank you.